Hi everybody! Let's continue our series on modeling 3D scenes using shaders and Raymarching technology. In the previous parts, we managed to render the scene from any position and at any angle, which is very useful in itself, but we are still rendering each object in the same plain color. This time, we'll fix that detail and refactor our code so that we can assign a different material to each model. Just like in the previous episode, I'd like to remind you that if you've just come across this video and haven't seen the previous parts, I highly recommend watching them first, especially if you are not very experienced in this topic. The description of this video should contain links to all parts. And of course, I will also add the source code to my product Godot Shader Pack, which you can get in my Gumroad store and which I regularly update with new shaders and other useful code. So, as I mentioned, we'll be using materials in this tutorial, so we need to define them somehow. I have the shader code open here in the state that we left it at the end of the previous part. There's only one difference. The parameter light color 1 has a default value of vector 3111, which means white. Just to be sure, check in the inspector to see that this parameter is indeed set to white. So I'll start by creating a new structure for the material data. It will have a total of 5 components, which I'll describe one by one. So let's do it right after this constant. It would be struct called material, and we will define its components. Like 3, ambient, vec3 diffuse, vec3 specular, float, shininess, and finally float dist for distance. Okay, I will get to the explanation briefly. And it will be probably useful to define a structure for the light source as well, since it's already made up of 3 parameters, as we can see, source, color, and energy, so that we can pass them between functions more easily. Let's do it here. Struct light, and the components are vec3 source, vec3 color, and float energy. Cool. Excellent. We can continue. The functions for rotation and sign distance fields will remain unchanged. Rotate X, rotate Y, rotate Z, and then sphere, cylinder, cuboid, and yeah, that's it. Unchanged. So I'll scroll down to where we have the functions for union, intersection, and the difference. Here, union SDF, intersect SDF, and the difference SDF. These need to be, this will need to be improved so that they also work with materials. In the previous version of shader, it was enough to know just the distance, float values A and B. Whereas now we also need to know the material that should be used. So let's define them like this. So as I said, we'll be returning material, not float value. So it would look this way, material, and let's call it, for example, union without the SDF suffix. And the parameters are material A and material B. All right. Okay, and now what we have to do is to compare the distances from these material structures, but return not the distance, but the material with the shorter distance, I guess. Yeah, this is union, so it's shorter one. So let's do it. If A dist is less than B dist, then we want to return the first material, otherwise return B. Very well, so this is the union, and let's do the intersection and the difference in the same way. I think I can just copy and paste this function, rename it to intersect, and change the less than to greater than. Now it is intersect, and for the difference, we know that this is simply an intersection with the complement of the second object. So it would be a little bit more complex, but in fact very easy. Material difference, material A, material B, and we will use the already existing intersect function. So return intersect and be A, and now the complement of the material B. So it would be a new material with these parameters. All of them are taken from the B, so B ambient, B diffuse, B specular, B shininess, it didn't change, and now the distance is the negative distance, so it's negative B dist. Cool. We have the basic functions, and now that we have the functions for combining objects in the scene ready, we set up the scene itself, that is, the objects using SDF functions. Again, instead of returning just distances as we do it here in the former SDF function, we want to return a specific material, so it will look like this. For simplicity, I'll start with just a single sphere. Let's do it below the SDF function, material, and call it material SDF, vec3p, the point, just like before. And now we'll start with the ground. Material ground is material. And what was the first one? I think it was ambient color. Vec3, 0. I think this is cool. This is okay for the ground. Now diffuse, let's make it a shade of gray, so Vec3.5. Specular, I think the ground shouldn't be specular at all. So again, it's a black color and also no shininess. And finally, for the distance, we'll simply copy the distance function from here, which is p dot y. Very well, we have our first object, and the second one, as I said, will start only with the first sphere. So let's create a sphere. I think I can again copy and paste and call it sphere 1, and this time I think it should have some kind of ambient color. Let's try a very dim shade of red, so it would be 0, 0, red, green, blue. For the diffuse color, we'll make it a red sphere 1, 0, 0. Now for the specular, I think it can be a little bit specular, 0.5, and let's make it pretty glossy, 10 for shininess. And finally the SDF function, and we copy this one instead of p dot y. Okay, very well. I think let's keep it as it is. And finally, we need to combine them and return the result. So material result would be, as we know, a union of these two elements, sphere 1 and ground. And let's return it. Return result. Great. Okay, if we take a look, we don't see any changes, of course, because we are still using the original Raymarching function. This one, which is calling the original SDF function. So it's time to introduce changes to that as well. To understand what we want to achieve, let's start from the top, that is, from the fragment function. As we can see, the fragment function determines the length of a given array, that is, the distance from the camera to the surface of the nearest object in the scene, and then calls the getLight function to compute the pixel color based on lighting. Our algorithm will be now more complex, so we'll move the entire logic into the Raymarch function, which will no longer return just the distance, but the final color instead, like this. So I think we can keep all of that and only change this to vector 3 and get rid of the other parts of the code. Yeah, this. At this point, of course, the shader can't be compiled, so let's move to the Raymarch function and modify it as well. First, I'll write it out and then I'll explain the differences compared to the previous version. Okay, so here it is, and we are returning vector 3. And now D, this is the same. Okay, P. And now, instead of this, we are creating the material. So let's get rid of that. And material is material SDF applied on the P. And D is increased by the material.dist. It is included in the structure. Very well. Now, we will fix this if... Let's use an absolute value because the distance could be a negative number if we are inside the object, and in that case it could create some unwanted artifacts. So this is safer. Material dist is less than our surface dist variable. Okay, and now vector 3 normal is get normal. This is the normal vector we will need for the correct shading. P, and yeah, it's compliant because the get normal is after this definition. So let's cut that and paste it before Raymarch. Now it's correct. And now the color. So vec3 color will be the function getLight. GetLight. Its parameters: material, B, array direction, normal, and our light source. And since we created a new structure, we can do it here like this: light, okay, with the parameters light source 1, light color 1, and light energy 1. Okay, this is the color. And finally, we can return the results. So return vec3 color. It's not necessary, just color. It's already a vec3. Very well. And of course, this cannot be compiled as well, but we'll get to that very shortly. All right, and finally, if D is greater than max distance, we just break the cycle. This is correct. And we have to return a vector here as well. So instead of D, we will simply return the 0 vector for the black color. Okay, so as we can see, the basic principle hasn't changed. Just like before, we extend the array in a loop, this one, and determine the distance to the nearest surface. However, this time we get the entire material, from which we use the dist field for the usual calculation, and then pass the material object to the getLight function, which will be responsible for calculating the final color based on all the parameters of the given material. Note that the call to the getNormal function hasn't changed, and it still takes only one parameter, the point where the ray intersects the surface. However, if we look inside the getNormal function, we have a small problem because it still calls the original SDF function. So we want to replace it with the new material SDF function. Let's write the function like this. So instead of that, it would be material SDF, and from that we take the dist field. Okay, this is distance, and of course we need to change it in here as well. Let's click copy and paste and use the dist field 1, 2, 3. Okay, that should be fine. And we also need to improve the getLight function. This time it will be a much more complex change, so I'll first write the skeleton of the function and then explain each line separately. And since it is just such a big change, I will simply delete the original getLight and write it here from the scratch. Okay, so vec3 getLight, and as we know already from the Raymarch code, we need these new parameters, sorry. material vec3 p vec3 3 rd vec3 normal and the light source, which is the light structure. Okay. And now the implementation. Let's start by determining the direction of the light ray. This part hasn't changed, it's the same like in the previous version of this function. Vec3, let's call it light there, is, and the normalize vector, because we are interested only in the direction, not the length, light source, and minus P, and I wonder why this is data vec3 getLight. Material. Light, sorry, typo. Lowercase I. Okay, very well, let's continue. And now we'll perform a calculation known as the Phong reflection model. If you're interested in the details, I recommend reading the article of the same name on Wikipedia, which explains everything in depth. For our purposes, it's enough to know that the final pixel color is determined using 3 components: ambient, diffuse, and specular, just like in our material structure. In fact, we'll be using an approximation of this model, which is also referred to as Phong shading. So let's start with the ambient value, which can be simply described as the color of the model in areas that are not illuminated. This will just be a direct assignment of the ambient value from the material structure. If we were using emissive materials that emit light themselves, we would multiply this value by the appropriate coefficient, but in our case, that's not necessary. Let's do this. Vec3 ambient is simply material.ambient. Okay. Next, we have the diffuse component, which is the color directly affected by the incoming rays from the light source. We already calculated this color in the previous version of the function, so we know that we need to consider the angle between the light ray and the normal vector, that is, their dot product. We also ensure that this value is never negative, and then incorporate both the diffuse component from the material structure and our light source. Let's do it. Vector 3 diffuse will be, as I said, we want to make sure it's not negative, so maximum of 0 and the value dot product, as I mentioned, between the normal vector and the light direction. Okay, and this we want to multiply by our diffuse value of the material and by the light color and by the light energy. Cool. All that remains is to calculate the specular value, which corresponds to the shininess of the given surface and its ability to reflect light rays. This calculation is a bit longer, so I've split it into 4 lines. First, we'll use the built-in reflect function to calculate the direction of the reflected ray. Vec3 reflection is reflect of light there and normal vector. Okay, this is the reflection. Next, we determine the angle at which we see this reflection from the camera's point of view. For this, we'll again use the dot product, which will apply to the previously obtained vector and the RD vector, that is, the ray direction. And by the previously obtained vector, I mean, of course, this reflection vector. So, float specular angle will be max. Oh, again, we don't want negative values. Dot product and reflection int ray direction. Here. Alright, we continue by determining how strong the specular highlight should be using the last component of the material structure, the shininess, along with the power function. We again clamp the results to the 0 to 1 range to avoid overdoing the highlight. So float specular power is clamp of the specular angle, as I said, power function. Pow, specular angle, and material shininess. We are finally using it, and the range is 0 and 1. Okay, and finally, from all these values and the energy of our light, we calculate the value of the specular vector. Vec3 specular is specular power times material specular vector times light energy. Perfect, and let's return the sum of these components. Return ambient plus diffuse plus specular. All right, and let's take a look. Nothing yet. Yeah, sure, I got some errors here. Let me fix that. Of course, vector 3, color. Yeah, we are not returning this, but color. There was a typo, and we can see it already here. Our first model with a real material. We can now test changes to the lighting parameters in the inspector, as well as the material parameters directly in the code. So, for instance, let's change the light energy. I think it's too dark, it's brighter, or darker. Or we can change the light source coordinates. Move it elsewhere. We can see how it turns, and the specular dot right here, which is pretty cool. Or if we change the light color, it should be reflected on the ground, which doesn't have any ambient color, and the diffuse color is gray, so it perfectly follows the light source color. Okay, and what about the definition itself of the sphere? We have it here. So let's change the color diffuse to red and blue, which is yellow, or we can change the specularity, shininess, or make it higher. Yeah, now it's pretty shining, but I think the red color was a bit better, so let's keep it at the red one, and we can keep it like this, no problem. Very well. But something is missing here, right? Yes, there are no shadows. In the previous version of the shader, we calculated shadows directly in the getLight function. Let's find it again. Where is it? Here. GetLight function. Because it was an elementary shadow with sharp edges. This time, we'll use what's called soft shadows and separate the relevant calculation into a new function called getShadow, which I will write just before the getLight function. By the way, a shadow is essentially just a result of multiplying a color by a value between 0 and 1, which darkens it. That's why it's enough for the getShadow function to return only a float value, and it works pretty much the same way as in the previous version, with one small difference. To achieve penumbra, or soft edges, at the boundaries, we'll add a new uniform parameter called shadow sharpness. Let's do it here. Uniform float shadow sharpness with a hint range and the initial value. Let's put it to 5, for example, and let's make the range from 5 to 50. Okay. And next comes the getShadow function, as I said right before the getLight function. It will do exactly what I just described, so I'll simply write it out. Okay, float getShadow with parameters vec3 p for the point of intersection, vec3 normal vector, float sharpness for the shadow edges, and light for the light source. All right, let's start. Float shadow starts at 1. That's because if there is no shadow, we'll be multiplying the color by 1, and that means no change. And let's return shadow to get rid of the error, and again, sorry, capital I, no, lowercase I. Great. All right, as we know, we need to add some small distance so the shadow is correctly calculated. This is exactly the same as we did in the previous part, or previous parts. I think the shadows were introduced in the part 2. And now let's start the calculation. So float shadow distance is 0, 0 at the starting point, and vec3 light there. Again, I think we can copy it from here. Light there. Okay, and now we'll use the Raymarching technique again to calculate the shadow ray. For I from integer, I from 0, I less than max steps, I plus plus, vec3, let's call it shadow point, is simply p plus light there times shadow distance. So we are following the ray of light, but in the opposite direction, to find if the original point is in the shadow or not. Material is material SDF, and we are using the shadow point. So where is it? Here. And now again, if abs of material dist is less than surface dist, we will return 0. We are in the complete shadow. And if shadow distance is greater than max distance, let's break the cycle. Break. Okay, and we need to we need to increase the shadow distance by the currently obtained material distance from the SDF function. Okay, and now the soft shadows. It is a simple calculation. Shadow is the minimum value of shadow and sharpness times material dist divided by shadow distance. Okay, and that should be everything, I guess. And we need to use this as well. So I'll modify the last line of the getLight function. Let's get here, and what we need to do is to apply the shadow to diffuse and specular color, not the ambient. This is not affected. Times get shadow, parameters P, normal, shadow sharpness, and our light. Okay, wait for it. And if we take a look at the scene, yeah, we can see there is already a shadow. And I think it already has the penumbra at the edges, the soft shadows. So I guess this looks pretty cool. Maybe too dark, but I'll get to it shortly. Very well, let's get back to the code. Okay, and I think I found the problem with the illumination. It seemed that the light source position was too close to the sphere. So I changed that to 0, 5, and 2. Now it looks a lot better. Very well. So all that remains is to add the other models to the scene that we had in the previous part. And to speed things up a bit, I'll just copy and paste the prepared code. So let me replace this function by this. And here it is. We have our sphere, our combined model from the cube and two spheres, the cylinder and the cuboid. And you can see how some of them are shinier than the others because I use different parameters right here in the code. We can see it as a part of the experiment, and then our use of difference, intersection, and other unions. Very well, I would say we are done, and maybe the scene is still too dark, so I think we can introduce the gamma correction. Let's do it here as a new uniform parameter, uniform float gamma with a hint range, and I think the usual value is 2.2. I think it's taken from somewhere. I don't know exactly from where, but it works pretty nice. Let's make it from 0 to 5, for example. And now all we have to add is this. Let me just, I think I'll copy it from here because I forgot completely the formula. So let's copy and paste. Okay, and now it definitely looks more natural. And we are done. As you can see, I assigned a different material to each object, so it's easy to observe how everything works together. You might notice some artifacts in the shadows, which can appear in such cases, and one way to reduce them is by increasing the shadow sharpness parameter. Let's do it, for example, to the maximum, and maybe it looks a bit better. You probably also noticed that I didn't use the second light source this time. That's fine, since the main focus of this tutorial is on materials, and we've covered them thoroughly even with just one light source. Thank you very much for watching. I'd say our shader is already quite capable without having a significant impact on overall performance when rendering the scene. We still have plenty of topics ahead of us, for example, translucent and transparent materials, textured materials, 3D fractals, and so on. What I mean is, this series is definitely not over, and I plan to create more episodes. For now, take care, best luck with your projects, and I'll see you in the next video.